Here today I want to take a closer look at a subject which is very often overlooked in computer science. It's a concept that is very important, and not too many people seem to really be interested with it, and I think that's a bit of a human tragedy, and I want to do something about that now. So I'm going to explain bitwise shift operations. Now, every language has them because practically every computer has the ability to do this. And if you're working in some RISC architectures like MIPS, they don't have a native instruction to multiply or divide, which means that there's no hardware that performs that functionality on its own. It has to be implemented through software. And chances are, if you're using a RISC machine, you are running an embedded system or a real-time system, and you want to save time wherever you can. Now, the problem with the multiplication and division subroutines is that they are software implemented, and therefore they take a great number of clock cycles. And oftentimes you don't need anything more complicated than multiplying something by 2. So let's walk through the high-level version, or really the human-level version of what we're trying to do here. So let's say I have a number in base 10, 23, base 10, and I want to multiply it by 10. And we know that this is going to be 230. And why do we know that? Because we all learned, at least before Common Core came along, that any number multiplied by 10, you can just add a 0 in the lowest number space and move every other number up one space. So 23 becomes 230. Easy peasy. Now, what happens in a computer is when you shift something, and this is shifting. This is the exact same thing as shifting, except we're using, base 10 numbers instead of binary or base 2 numbers. So what happens in binary in a microprocessor is that we can take a number, say 6, 0, 1, 1, 0, in base 2, which is binary. And we all know what 6 times 2 is. Let me write it down here. 6 times 2 is 12 from our multiplication tables. And we want to get 12 without having to go through a big subroutine in our nice MIPS architecture. So how do we go from 6 here to 12 without going through that subroutine? Well, here's how it's done. Let's write out 12. All right, so here's the 1-bit, the 2-bit, the 4-bit, the 8-bit. So to get 12, we need to add 8 and 4. So that's 1, 1, 0, 0, 2. And I'm just adding these 2's to keep straight what what base we're using for each number. There's nothing actually special about these. But hang on, looky there. It's the same number, almost, with just an extra 0 added in. And that's all bit shifting does. It just moves everything over 1. So now, instead of having 6, we can, in one instruction, in assembly language, mind you, shift out that 1, or shift out that 0 here, because we're using a very small value. And suppose we have 32 bits, and we know that the program isn't going to get so big or so complex that such a large number would be necessary. We can just shift. And in MIPS, the instruction is shift left logical. And you have your destination register, your source register, and you have a what is called a shift amount. So when the value of your source register is 6, the target register, or the destination register, will take on 12. And that's how you shift left to multiply. Now, shift left, or shifting right to divide is the exact same operation in reverse. So now let's say we have 230, and we want to divide it by 10. Well, we know, there, get rid of those, and we have 23. Just try consistency here. Now, in order to do something similar in programming, let's say we have 10 in binary, 1 0 1 0, and we want to divide that by 2, 0 0 1 0 2. So what we would do, instead of running it through the division subroutine, which would take about, in a 32-bit architecture, the division subroutine takes approximately 16 instructions, or 16 cycles over an untold number of instructions, 16 loops. In MIPS, it's very hard, or very time consuming to write that. In ARM, it comes a little easier, but ARM also has native division and multiplication subroutines, so there's not much use for, well, most ARM instructions have that, but I digress. The general idea is that we want to divide 10 by 2 and get 5. Well, let's write 5 out. 0 1 0 1. Hang on. We just moved this over. And what happened is, way back at the end of, or the highest bits of this register, there's a bunch of zeros here. Way back at this end of the register, there's a bunch of zeros here. Well, looky here what we have. We just added in another 0. We moved all of these over 1. Move that over 1, move that over 1, move that over 1. And what is really going on here is we are essentially dividing it by some power of 2. So in the case of 10 divided by 2, we are actually saying we want 10 divided by power of 2 to the first power. If we wanted to have 10, or say 16, 16 is a nice square number, and we wanted to divide that by 4, we would say we want 16 divided by 2 to the second power. The square of 2 is 4. 16 divided by 2 to the fourth power. But hang on. If we moved in 1 bit here to divide by 2, what if we move in 2 bits, shift from the left, or shift right 2 bits? Well, let's write out 16. All right, so we have 0, 0, 0, 1, 0, 0, 0, 0. Okay, and we want to get 4 out of this. Now, what is 4? In this example, in any example really, 4 is this. But hang on, here's there. There it's, we just have 1 bit there and there. What we did was we moved everything over 2. Now, obviously you can see the limitations, because if we're moving all these over 2, then these 2 bits here, they get shifted out. They disappear. And unless your architecture supports things like overflow detection or carryover detection, you're going to lose that information completely. So in division, it's not, when you're using right shifting to divide, it's not as big a deal, because assuming you have an int here, what you would call an int in a high level language, you know, let's say we have some weird number like 15, okay? So 0, 0, 0, 0, or let's say 15, 1, 1, 1, 1 in binary, and you want to divide that by 4. Well, 15 divided by 4 is 3. But we also know that this is going to look like, that 3 is going to look like this. So it's perfectly okay whenever you're dividing by ints, when you're dividing with ints, to actually just shift these lower bits out and lose them forever, because the same process in if it compiles naturally, if you compile this operation naturally, you would get the same result as if you had just shifted out a bunch of bits. And most high-level languages don't actually let you shift double or floating point values, which is kind of tragic because even C doesn't allow that, and C is pretty cool about letting you do almost anything you want, but it doesn't let you shift double values or floating point values, which, get off my soapbox in a second or two. It should allow it. I can see why they wouldn't want to allow it, because floating point values are laid out differently, and you can really corrupt your data if you don't know what you're doing. But it would just be cool to do that. Oh well. C doesn't even allow you to see the actual binary representation, I don't think, unless someone wants to correct me if I'm wrong. Now, lastly, I want to talk a little bit, at least, about how you can use left shifting for multiplication purposes. And now this is what's really going to just tickle you inside, because in, as I said, MIPS architecture, there is no native multiplication operation. No hardware exists to perform multiplication. So whenever you're writing on what is going to ultimately be on a MIPS processor, you want to save as much time as you can. So what we have available is left shifting. So let's say we want to divide 17, or no, sorry, let's say we want to multiply 17 by 5. Actually, let's say 8 by 5. 8? No. Let's say we want to multiply 9 times 5. And really, this 9 could be any variable x. So we don't know what x is. Here it's 9, but in another loop, it could be 23 or 5 million. Who knows? But we do know that it needs to be multiplied by 5. So we know in this particular case, it's going to be 45. What happens, though, is it's going to go through in your MIPS console through a very long subroutine. We want something faster. So if we shifted this x two places, or 3 places, that would be the same as multiplying it. This is logically equivalent as 8x, because here we are essentially taking x and multiplying it by 2 to the 3rd power, which is 8. This is 8. Okay. And what we also want to do at the same time, or really on the same line, is take x again and left shift it once. And that's logically equivalent to multiplying x by 2, which is really x to the x times the first power of 2. But hang on a second. We're starting to see a pattern develop, because we know from high school algebra there is a way to combine these two and let's say we have a function here, 8x, and some mystery function here, and 2x, and we want it to be equal to 10x. So what do you think this is? That's right, it is addition. Nice interrobang for you. So if we add our multiplication of x by 8 and our multiplication of x by 2, we would get multiplication of x by 10. And that carries over seamlessly into our computer program, because we can just say return, never trust the computer guys to spell correctly. I was up late last night writing a C program, and after a while everything looked wrong. The way everything was spelled, just wrong. So we've got our return statement here, and we don't want to go through that big expensive multiplication subroutine. So what we can do is x3 plus x left shifted once. And there you have it, how to multiply by 10. And you can carry this into any functionality you want. Let's say you want to multiply everything by 17. Well, okay, so we know we need to get 17 through powers of 2, and we know that if we increase this power to 4, so we have 2 to the 4th, 2 to the 4th is equal to 16. Well, then looky there. Our return value gets even easier, because we can actually leave out one of the shifting operations and just say x plus x left shifted 4 times. And in the next video, I'm going to show you exactly how much that will save, how much trouble that will save. Thank you and have a great day.